Hi, my name is Bo. This is a joint work with Ting Wei, Yin Lin, Jeremy, Tai Jin, and Meng Mi. Visual search is a challenge problem in natural vision. Here is an example visual search trial with eye movement recorded. This person is searching for a calculator. The yellow dot denotes the eye movements, and the red rectangle denotes the ground truth target location. After looking around for a while, this person eventually managed to find the calculator efficiently with a few number of eye fixations. In this visual search trial, you might notice that the target calculator looks different from the calculator on the search image. It varies in its pose and geometric transformations. Sometimes the target objects that the subject is looking for might even be completely novel. Humans have no problem quickly generalizing this concept of novel targets and perform visual search on these novel objects with zero-shot adaptation. In practice, the visual search problem can become even more challenging. Instead of looking for one single target, we might be asked to looking for multiple instances of multiple target types. Going back to this search example, we might be asked to look for cups and keyboards in addition to the calculator. In visual search, not only target visual features matter, but also their values. What if I tell you that these items carry different values? Collecting high-value items will lead to higher cash rewards. How would your search strategy change with different target prevalence and values? Here, we are interested in study what are the brain computations that ensure time-efficient hybrid visual foraging across varying target prevalence and values. Computer vision researchers have devoted great efforts in developing object detection algorithms. However, we realize that this approach relies on exhaustive scanning of the entire image. In order to get the bounding box and the class label of each object, it often requires extensive supervised training. Consequently, these computer vision algorithms were inefficient and showed poor generalization to search for novel objects. Moreover, they failed to take into account the value modulation of target types. Thus, we spearheaded a neuroscience-inspired approach to tackle the problem of hybrid visual foraging. To benchmark AI and human performance in hybrid visual foraging tasks, we first design and conduct human psychophysics experiments. Here is an experiment schematic. For details, please refer to our paper. Depending on the number of target types, target values, and target prevalence, we introduce several experimental conditions. These include unequal value and unequal prevalence, where the most valuable items were 16 are less prevalent with a proportion of 7% in the search array. We also include other cases where the target of the same prevalence carry different values, or the items carrying the same values are of unequal prevalence. To benchmark AI performance in the same set of tasks as we test on humans, we train the model only on 2 conditions and test the model on the remaining conditions in the orange box. To probe the decision-making process of humans in hybrid visual foraging, we developed a computational model named Visual Forager. The model takes target image, search image, and target values as inputs and outputs both mouse clicks and eye movements. We train the model end-to-end via PPO in reinforcement learning. Please visit our poster for more details of our model architecture. Let us look at some interesting results. Here, we report the normalized score. Under uneven value and equal prevalence conditions, humans achieve a normalized score high above chance in black. This implies that humans are very proficient reward forager. Similarly, our VF model in blue also surpass other baselines and achieve cumulative rewards comparable to humans. This observation is consistent across other experimental conditions. Here are the conclusions. Please scan QR code for more information.